Sushi rating and ranking. The reason I did this project is because I was looking at fine-tuning for large language models, and it uses exactly the same structure of data I'm going to tell you about. So let's look at what that is. So I'm going to start with a little preview here before we get on to the actual data, which is the Bradley-Terry model on which this is all based. I'm not sure if we have this in the user's guide or not, but like Andrew Gelman often said, if you build a model these days, there's a very good chance some psychometrician built it in the 1950s. So the Bradley-Terry model, which was reinvented as the ELO model like 15 years later, was early 50s, modeling consumer preferences. They asked a bunch of consumers, do you prefer this soap to that soap? And they gave them sort of a mixed panel of data. So you've got a bunch of raters, you have a bunch of items. You ask people, which one do you prefer? Yij is going to be equal to 1 if item I is preferred to item j. Then for each item that you're considering, it gets a value, just a parameter alpha. That's not going to be identifiable as it is, so we either need to set the sum of those to be equal to 0, or we have to have alpha 1 equal to 0 to identify this. Good news, thanks to really cool work by Sean Pinkney here, we have a really good sum to 0 constraint coming out in the next version of Stan. So this will be a lot easier to actually code and more robust. But the model is very simple. The model is just a logistic regression with item effects. You're basically saying the rater is going to prefer item I to j is just going to be the inverse logit of the differences of their qualities, if you want to call alpha that. So it's just going to be the normalized exponentiation of alpha I over alpha I plus alpha j. That's the probability that a rater is going to prefer I to j. So the sampling distribution is just this. This is a widely used model for consumer preferences, right? Often what we're going to have in these cases, we're going to have partial panel data. Not every reviewer, every rater is going to rate every pair of items. So I'm going to introduce some notation where we're going to have n rankings. And then it's going to be a ranking of item AN and item BN. And then the sampling distribution is here. We're just going to be looking at alpha sub AN minus alpha sub BN. The idea is A picks out the first item, B picks out the second item, right? And alpha AN is just used for readability here, right? So this is pretty standard, I hope. So let's look at the data that I'm actually going to be analyzing today. And like I said, this is just like the data you get for fine-tuning for GPT. They give people GPT outputs, ask them to rank them and rate them, and then they push that through preference optimization. So in this case, we have a data set from 2003, which is really cool. They asked 5,000 Japanese people what their favorite sushi was in the following way. They picked 100 different kinds of sushi, like fatty tuna, shrimp, so forth. And then for each rater, they gave them a random 10 pieces of sushi and said rank them in order of your preference and rate them on a 1 to 5 scale. So you get both pieces of data, both ranking data and rating data for them, right? This is, like I said, the same human feedback that OpenAI used to align ChatGPT. They gave people ChatGPT outputs and said rank them in order of which one you think is best and rate them all on a 1 to 5 scale. Right? So that's just the notation for this, right? This is all being driven. So how many people have seen the Plackett-Luce model before, which extends Bradley-Terry? Nobody, great. I hadn't seen, the reason I did this case study is I had never seen this model before. I was just in an LLM meeting and everybody was using it, and I'm like, I better go learn what this is. It all follows from the Luce axiom here, which is something Luce, I think, introduced in the 1950s. The idea is that if I have a set of items and I'm making a choice among them, those choices and probabilities have to be consistent under taking subsets, meaning if I have a probability distribution of some big set of items and I restrict my attention to a subset of them, the probabilities have to be in the same proportions to each other. So I have an example here. If you have 3 ice cream flavors, vanilla, chocolate, and strawberry, let's say they're 0.7, 0.2, and 0.1 is the probability that you're going to choose one of those at any given time. Then if I give you just chocolate and strawberry, then the ratings have to be proportional. So I've just standardized them and normalized them there. So it has to be a 2/3 to 1/3 ratio because that was the ratio of chocolate to strawberry when I had 3 choices. Right? So that's all the Luce axiom is saying is you be consistent under sub-choices. The items you're selecting among always have the same proportional probabilities. This is a fairly, any kind of assumption like this on human behavior is a pretty strong assumption. People aren't consistent like this. right? So this is in some sense wrong. This is just like our clickers at work. They're very counterintuitive. So the Plackett-Luce model of rating is just an iterative Bradley-Terry model. The idea is I'm going to give you a whole bunch of things to rank. So this is a ranking model, right? And the idea is what's going to be first ranked. I'm going to pick that out by giving everything a quality, and then I'm just going to exponentiate those and normalize them. So the probability of ranking item 1 ahead of all the other items is just the exponent of alpha 1 divided by the sum of all of those things. Right? So it's just a multivariate generalization of the Bradley-Terry model. We give everything a probability, and now we're doing essentially softmax to decide which ones we want to actually use. The ranking model is exactly sort of what you would expect if you think about it. We create a ranking in the following generative way. We have a bunch of qualities among the items. We find the probability of the highest rank item. We select it. And then we iterate. We go on to choose the second best item. We look at what's the probability that the rank of the second item is greater than all the other ones. And this all just normalizes down by those probabilities in the Plackett-Luce model. Right? So the idea is we have preferences among items. We choose the first one. We choose the best one according to that probability distribution. Renormalize, choose the next one, iterate till we've generated the whole ranking. Right, so the stand model for this, this is just the this is just the sketch to see the data. So we've got I items, we've got K items ranked per raters, we have R raters, we have the rankings that are actually given to things, which there's no way in stand to make that like consistent to say this is we don't have a permutation data type, which is really kind of what this should be. And then the parameters here, I've reduced them to a simplex, right? It's normally stated on the log odds scale, but in stand it turns out to be easier to specify this for identifiability. It's just assigning beta as a simplex. The problem is when you have log odds scales parameters and you run them through softmax, it's not identified unless you enforce some other constraints, which comes sort of for free by using the simplex type here. So this simplex is going to represent the preferences when all the items are in play, right? And the model's just going to say for every one of our ratings is going to be distributed according to the Plackett-Luce distribution, which I'm going to show you on the next slide. Right? So the Plackett-Luce density turns out to be really, really easy to write in stand. It's not particularly clear right away that this is the right thing to do, but it's an efficient implementation of this. Right? So this directly codes the Luce axioms where we're taking alpha. Right, oh shit, this is this thing going backwards. Right, so beta, normally we're thinking of softmax of alpha equal to the exp of alpha over the sum of the exponentiations. That's what our beta is actually equal to. Right, so if we think of alpha, that's going to be equal to log beta here, where alpha is the log odds probabilities. Right, and the Plackett-Luce density is just a product of all these fractions. So if you look at what's going on here, it's just multiplying each preference in order, right? And that's what's going on here, right? If we look at the second line there, we're taking the cumulative sum of the betas, right, which is giving us the denominators. We're taking the betas that we actually have in the denominator. We're doing element-wise division. Right, so beta y is indexing the numerators, and the cumulative sum indexes all the denominators. So if you look at what's going on here, each one of those has a numerator, and each one of those has a denominator based on everything that's left, and that's what's getting calculated with this here. So it's very easy. So what's the answer? Right, well, first of all, the fit. The fit's very good. This is just 50 warm-up and 50 sampling iterations, which I realized when I was doing this, that was my like draft mode, and I never took it out of draft mode when I generated this. But that's fine, because when we're done, we have an effective sample size of like 30 or 40. This is a very, very easy model to fit with this data that I actually used. So this is fine. 30 or 40 effective sample size is fine for inference. You don't really need more than 100 iterations. Right? Our default's 1,000 warm-up and 1,000 sampling. You don't need to do that for most problems. Right? And you can see that the posterior intervals are fairly tight in terms of standard deviation and what the 95% range are. Everything fits really well. So what do we get for best sushi? Well, it turns out Japanese people really like tuna, and especially they like fatty tuna. Right? So it's mildly fatty tuna, tuna ground up into a roll. And they're way out ahead of everything else. And then shrimp and prawn and salmon, the one I actually really like the best. So anyway, the central 90% intervals are very tight. So these are pretty well separated until you get down to ones that are like here that are really close to each other. Right? The data is not really giving you a lot of certainty about these preferences. And as somebody pointed out to me before, this is probably the wrong model in the sense that you probably want a mixture. It's not like, not everybody has exactly the same preferences. This is just getting some kind of consensus preference over the whole population. Right? And the worst sushi, who knows they even made things out of this. The last stuff's just all stuff they scraped off the bottom of the ocean that's all rubbery, plus weird things like okra. Who puts that in sushi? Eggplant? Yeah, nobody likes this stuff, so. Oh, sorry, I'm going backwards again. Okay, so now let's look at the ordinal. So that was dealing with the ranking data. Now let's look at the rating data. This is just an ordinal logistic model, right? We have qualities for each piece. And then we have cut points, C1, C2, C3, C4. We're doing a 5-way rating, so we need 4 cut points. And we just use an ordered logistic distribution here. Right? The idea is we have quality, and then the probability of them giving it a ranking from 1 to 5 is determined by this ordinal logistic. I have a plot here trying to illustrate how the ordinal logistic works. Right? The idea is that the black lines are a standard logistic distribution centered at eta, where we have -2, 0, and 4 in the 3 facets. The blue vertical lines represent the cut points. Thanks. And then the probabilities that you're going to return 1, 2, 3, or 4. For some reason, I only did this for 4 instead of 5, but it looks the same with 5. It's just the area between the lines under the distribution curve. That's the proportion to which you choose these things. So the area under the density between the vertical lines corresponds to the probability of choosing that item. Right? It's all standardized because it's a standard distribution. Right? So the ordinal logit in STAN is really simple because we have the ordered logistic distribution built in. Basically what we do is we just have a bunch of item qualities. We're assuming they sum to 0. I'm using our unreleased, I didn't actually use this in the code, but here for simplicity, this is what we're going to be calling the new type, sum to 0 vector for eta. And then we're just giving these weakly informative priors on the cut points. We could put a prior that makes sure the cut points are separated from each other. Right? We could put some kind of like log normal or gamma, 0 avoiding prior but on the differences between the cut points. But we don't need to do this here. This model, this data is very nice. It fits really well. Right? What's the fit look like? Well, the fit's, again, very good. This fits even better. This is 50 iterations, and we're getting more than 50 effective sample size. So this is fitting very, very well. And the top 10 comparison, it looks pretty much the same. So they were pretty consistent between the rating and the ranking. Right? And they're a little different. I've put both of them up here. Right? The coefficients tend to be a little less separated in the Plackett-Luce model, so I plotted the coefficients against each other to see what it looked like. Right? This is the ranking and rating coefficients. And on the right, I'm like, because what I want to do is I want to put this data together with one set of shared parameters. Right? So what I'm seeing is that the relation between these is that the log of the ranking is roughly linear in the rating. So all I'm going to do is say, let the parameter for the rating model equal alpha 0 plus alpha 1 times beta. In other words, I'm looking at this and I'm saying there's a linear relationship between these parameters in the 2 models. This is the parameter in the ranking model. This is the parameter in the rating model. They're linear related. I'm just going to assume that. I'm going to introduce new parameters, alpha 0 and alpha 1, and I'm going to fit those along with everything else. And then I'm just going to throw both data sets together. I'm going to use both data sets, both likelihoods with a shared set of parameters. Right? Turns out, doesn't really make much difference in this particular thing. If you look at the ratings, they're all very similar. And it turns out the fits wind up being much closer to the Plackett-Luce, but that's because that's the scale I put the declaration of the parameters on. Right? So that's not particularly surprising. So what's missing from this? This is a very, very simple model for this. What haven't we done? Well, we could start grouping the ratings. What we've done is we have 5,000 people. We just piled them all together. The fact that we know that all 10 of these ratings came from the same person is something that we could use. Right? But 10 isn't a whole lot to do that. right? Crowdsourcing problems like this are actually what got me into Bayesian statistics. That's what got me talking to Andrew in the first place. The raters come with covariates in this data set. It's a really cool data set. They have region, they have sex. I don't know if they have age. I didn't use any of the covariates, but obviously you could be doing that. The items themselves fall into groups like tuna versus everything else, or fish versus, last slide, fish versus shellfish versus vegetable, right? We could do something like cross-validation evaluation. The obvious question to ask here is the model, the combined model, better in some sense than the other one? I didn't answer that in this talk, right? So there's still some things to do. The weakly informative priors seem fine, so I think it's okay to leave those. And that was the last slide. Thanks. Does whoever's doing the next talk want to set up while I take questions? Aki?
Just a question, but advertising my talk, you said 30 draws is enough.
Yeah.
Afternoon, I will tell you diagnostic that tells whether 30 is enough or how many you need.
Okay, excellent, excellent. Love setting other people up.
Oh, and I want to say that Brian Ward also, he wrote some beautiful C++ code for that.
Yeah.
To zero vector, so thank you.
Brian needed an excuse to learn C++, so. Is there one more?
Just to check I understood, in the joint model, the data kind of allowed to be inconsistent, so someone could have given a higher rating to one than another, but actually...
Sure, sure. It's whatever the people said is the data. So this model's pretty robust for sort of inconsistent ratings. It's just going to add more noise to the posterior when that happens.
I would love to see like the nutritional facts and which one, how much fat content.
Yeah.
You know.
Sure, that's another covariate you could add to the pieces. Yeah, salmon belly's in there somewhere, which is my favorite piece of sushi. Right.
The fact that you saw that these two systems of rating and ranking were like linear related, do you think that that would be true in general, or do you think that was just sort of a happy accident of this?
I think it has something to do with the parameterizations of them. Because you're exponentiating things in one case, I think that leads to that relationship, and that the qualities are just going to be sort of linearly laid out. But are they going to be exactly that relation? I don't know. It's a good question.
Let's thank Bob again.
Thanks.